is not the whole story. To understand the universe on extremely small scales, we have to use our other set of laws, quantum mechanics. And as we'll see, quantum mechanics paints a picture of space so drastically different from general relativity that you'd think they were describing two completely separate universes. To see the conflict between general relativity and quantum mechanics, we need to shrink way, way, way down in size. And as we leave the world of large objects behind and approach the microscopic realm, a familiar picture of space in which everything behaves predictably begins to be replaced by a world with a structure that is far less certain. And if we keep shrinking, getting billions and billions of times smaller than even the tiniest bits of matter, atoms and the tiny particles inside of them, the laws of the very small, quantum mechanics, say that the fabric of space becomes bumpy and chaotic. Eventually, we reach a world so turbulent that it defies common sense. Down here, space and time are so twisted and distorted that the conventional ideas of left and right, up and down, even before and after, break down. There's no way to tell for certain that I'm here, or both places at once. Or maybe I arrived here before I arrived here. In the quantum world, you just can't pin everything down. It's an inherently wild and frenetic place.
The laws in the quantum world are very different from the laws that we are used to. And is that surprising? Why should the world of the very small at an atomic level, why should that world obey the same kind of rules and laws that we are used to in our world with apples and oranges and walking around on the street? Why would that world behave the same way?
The fluctuating, jittery picture of space and time predicted by quantum mechanics is in direct conflict with the smooth, orderly, geometric model of space and time described by general relativity. But we think that everything, from the frantic dance of subatomic particles to the majestic swirl of galaxies, should be explained by just one grand physical principle, one master equation. If we can find that equation, how the universe really works at every time and place will at last be revealed. You see, what we need is a theory that can cope with the very tiny and the very massive, one that embraces both quantum mechanics and general relativity and never breaks down, ever. For a physicist, finding a theory that unites general relativity and quantum mechanics is the holy grail, because that framework would give us a single mathematical theory that describes all the forces that rule our universe. General relativity describes the most familiar of those forces, gravity. But quantum mechanics describes three other forces. The strong nuclear force. That's responsible for gluing protons and neutrons together inside of atoms. Electromagnetism, which produces light, electricity, and magnetic attraction. And the weak nuclear force. That's the force responsible for radioactive decay. Every event in the universe, from the splitting of an atom to the birth of a star, is nothing more than these four forces interacting with matter. Albert Einstein spent the last 30 years of his life searching for a way to describe the forces of nature in a single theory. And now, string theory may fulfill his dream of unification. For centuries, scientists have pictured the fundamental ingredients of nature, atoms and the smaller particles inside of them, as tiny balls or points. But string theory proclaims that at the heart of every bit of matter is a tiny, vibrating strand of energy called a string. And a new breed of scientist believes these minuscule strings are the key to uniting the world of the large and the world of the small in a single theory.
The idea that a scientific theory that we already have in our hands could answer the most basic questions is extremely seductive.
For about 2,000 years, all of our physics, essentially, has been based on, essentially, we were talking about billiard balls. The very idea of the string is such a paradigm shift. Because instead of billiard balls, you have to use little strands of spaghetti.
But not everyone is enamored of this new theory. So far, no experiment has been devised that can prove these tiny strings exist.
Let me put it bluntly. There are physicists and there are string theorists. It is a new discipline, a new, you may call it tumor. You can call it what you will. They have focused on questions which experiment cannot address. They will deny that, these string theorists, but it's a kind of physics which is not yet testable. It does not make predictions that have anything to do with experiments that can be done in the laboratory or with observations that can be made in space or from telescopes. And I was brought up to believe, and I still believe, that physics is an experimental science. It deals with the results to experiments or, in the case of astronomy, observations.
From the start, many scientists thought string theory was simply too far out. And frankly, the strange way the theory evolved in a series of twists, turns, and accidents only made it seem more unlikely. In fact, even its birth has been turned into something of a myth, which goes like this. In the late 1960s, a young Italian physicist named Gabriele Veneziano was searching for a set of equations that would explain the strong nuclear force, the extremely powerful glue that holds the nucleus of every atom together, binding protons to neutrons. As the story goes, he happened on a dusty book on the history of mathematics, and in it, he found a 200-year-old equation, first written down by a Swiss mathematician, Leonhard Euler. Veneziano was amazed to discover that Euler's equations, long thought to be nothing more than a mathematical curiosity, seemed to describe the strong force. He quickly published a paper and was famous ever after for this accidental discovery.